How do you create a self-learning agent? That's what I wanted to know earlier this summer as I was learning about agents, and that was one of the areas that I'm most interested in. I think a lot of us are interested in. So that was the motivation for creating this demo that you're looking at here. So in this video, I'm going to show you a self-learning agent in the context of this game. It's a game. I'll explain the game. And as I'm explaining the game, I'll explaining the self-learning aspect of the agent. I'm going to do just a quick introduction to this demo in this video, and in other videos I'll go into more detail because there's a lot in this game, which really surprised me as the development of this game evolved, and it's actually still evolving. I'm still in heavy development in this demo, but it's functional enough that I wanted to show you how it works. So let me just get started. So the way this works is that you can see that there's a game board here. It's a 5x5 grid, and there's 2 players. So you can have human players, which are mainly used for training agent players, and agent players are different implementations of or instances, not implementations, but instances of an agent. And I'll explain the difference between an agent and an agent player in a few minutes. But let me just get this game started. So I'm going to have, say, I can pick different pre-existing players, humans or agent players, or you can create new ones. But let me just pick one. I'm going to pick one agent that I set up for that uses Gemini 2.5 Flash as this model, and select that. And then I'll play it against Gemini 2.5 Pro as its opponent, and select that. And then once you begin the game, it's off. Now the game has multiple levels where the game board gets bigger. It goes from 5x5 to 7x7, 9x9, and so on. But surprisingly, I haven't been able to really get past a 5x5 because these models struggle to play this game, very surprisingly. So actually, we're off to a good start here, where the 2.5 Flash made its initial move. They learned pretty quickly that the center square on the board is the most valuable, strategically valuable. So it picked it right away. And then 2.5 Pro knows that it should start to block around that centerpiece. So now the game is off and running, and like I said, it's totally in auto mode because there's just 2 agents playing each other. Now the human agent is mainly for training, so I could play a new agent player to train it how to use the game. So the distinction between an agent type and an agent player in this game is that an agent player is defined as a specific instance of an agent and its specific model. So this agent type, that's implemented in code using an Akka agent component, is you can use any model that you want with it. That's one of the nice things about this agent model. And let's see. 2.5 Flash just scored. We got 3 in a row, and that's a scoring point. So the game's moving along. So it's that agent model association that makes a specific agent player. So this where you have 2 instances of the agent going here. One is 2.5 Flash and one is 2.5 Pro. So that's what's going on. Now the learning part is that each agent has its own what I call playbook. And this is the example of the current playbook for 2.5 Pro. And it's basically just a document. So these agent players have tools that they can use to read the playbook, which starts out empty, and then revise the playbook. And the model decides when to read it and when to write it. Now the system prompt and the agent of course, tells the model about these tools, and the system prompt does say to use the playbook tools that's the way it learns. So it does know that. Oh, this game's moving pretty quickly. A lot of times it goes pretty slow. So that's so each agent player has its own instance of a playbook. And you can see the other thing is that you can see that sequence ID here, that's the number of revisions that this agent player has made to its playbook. So while this game is running, and we're moving pretty, they've both scored, so that's pretty good. I'm going to go to a different tab and show you some of the other features of this game where there's more data that's getting collected. So another one is the Playbook Viewer, and this is where you can look at the sequences of playbooks, version by version, that was created by these agent players. So this is the latest one, sequence 16, 15, 14, and then just for fun, I added a diff to this so I could see the changes. How significantly is the model, the specific model, in this case 2.5 Pro, doing its changes? And you can see there's some, in some cases it significantly revises the playbook. In other cases, it's maybe not quite as significant. But that's the Playbook Viewer. Now, another piece of this game is what I call the leaderboard. And this is where it's recording each player and its history of games. So right now it's the top player that's won the most games, and that sound you heard was the game's over now. It finished. We'll look at see who won here. It showed in progress. So if I let it refresh, yeah, 2.5 Flash. This game just played. It's today. It's September 12th, and it's just before 8 a.m. my time. And 2.5 Flash lost. And you can see Flash made 6 moves and it scored once. 2.5 Pro made 6 moves and it scored 3 times. So you can see the winning score is, here's a win, here's a win. So there's a vertical line, horizontal line, and a diagonal line. So that's how the 2.5 Pro won. This was a pretty good game because both agent players were responding pretty quickly. But if you look at some past games, like let me go. Let's see. Here's a good one. This is the same, 2.5 Pro playing Flash, and it's playing against Pro. And look at the times. And I'll zoom in a little bit here. It's 1 minute to make a move, another minute, 37 seconds, minute. Sometimes it depends on the model, but sometimes these models can take many minutes to complete a move, a single move. All this time is think time. Think time is token time. Think time is money time, where the model providers are making money from you. And 37 seconds, a minute, 2 minutes, sometimes I've seen 3-4 minutes of think time to make a move in this simple game. It's just really surprised me. The other thing is that it's Gemini, the Gemini models seem to be the most well-behaved in my experience with this game, whereas the OpenAI models are okay, but they're much slower. GPT-5 and GPT-5 Mini is a lot slower. But the costs aren't that bad. The Gemini models are pretty economical. On the other hand, the Anthropic models, Claude, Opus, and Sonnet, I don't play those too much. They cost a lot of money, a lot. I mean, dollars to play a game, which is crazy. But that's the way it is. So that's what one of the big surprises for me is how much these models struggle to play this game. Even as they learn how to play the game, they think and think and think. One thing that really surprised me, and I can see this in the logs, is how often they're invoking tools, because it has these agents have 4 tools. There's a tool to read the playbook. There's a tool to update the playbook, as I mentioned. There's a tool to make a move, because the game logic is actually being handled by a Akka event source entity. That's where the actual state of the game is maintained, and moves are commands to that state, and the entity decides if a move is legal and if it's scored or if it won, those types of things. All the decisions about the state of the game is in that Akka event source entity. There's other entities involved here as well. And so there's all this activity that's going on within the game, and yeah, I don't know. It's just surprised me how much effort it takes to do things. So the time it takes, and then the other thing is that I'll show you the agent implementation itself is quite simple. That there's a this is, you implement it as a it extends agent as the type. I've got a hard-coded system prompt right now, but I'm going to make some fairly significant changes to that in upcoming revisions of this game. But the heart of this game is right here, where this is where the actual call is made from the Akka agent to the model. And you can see that this is where you pass in tools and the system prompt and the user prompt. But the big thing for me was hardening the agent to handle all the different kinds of things that these models do in their weird and wild behavior. Timeouts are often happening, but there's model exceptions, and you can see I've kind of hardened it with, based on the specific exceptions, should the agent player be allowed to try again, or should it forfeit the move? And I'm still tweaking and tuning this. In fact, I just added this null pointer exception where the model just responds with a null and it triggers a null pointer exception in the agent. I'm handling that as a try again right now to see how that does it. So that's basically it. Let's go back to the finished game, and we can see it took, this one really ran fast. It ran in 4 minutes and 16 seconds. But if we go back to the leaderboard, you can see some of the durations of these games. Like this game here is 11 minutes and 26 seconds. Two agents playing each other, 11 minutes and 26 seconds of think time to make, what, 15 moves. That's a lot of compute. That's not insignificant dollars either. Really, really interesting, right? This is what's kind of mind-blowing for me. Just playing this game, So makes me think that also is like, everybody says, oh, these models are going to take over the world. It's like, okay, well, this game is trivial for me or you or even a child, I think, to play. A human will figure out the rules of this game really fast and become very proficient at it very fast. And your think times are going to be in like single-digit seconds. These models are struggling with it. So really interesting, right? So it's been fascinating. The link to this demo, the GitHub repo, is in the description of the video. I really hope you got something out of it. I'd love to hear anybody try this and experiment with it and maybe make changes to it, try other models. I haven't tried Grok or some of the other models. Or just feedback. And so hopefully you enjoy it. Please like and subscribe, keep learning, and we'll see you in the next one.